Good day everyone and welcome. Today, we delve into the fascinating world of large language models with our presentation titled Large Language Models for Code Summarization. This research, led by Balazs Salantai, Gergo Saleh, Thomas Martin, Anna Syke, and Balazs Pinter, explores the untapped potential of these models in the realm of software engineering, particularly in summarizing and explaining source code. Stay tuned as we unravel the capabilities of these models and the need for further research in this exciting field. Thank you. Our investigation centers around open-sourced large language models, with a particular focus on their code-to-text capabilities. We aim to understand how these models handle source code in relation to natural language text. The application of encoder-decoder architectures in these models has been instrumental in software engineering tasks. Models such as GPT-4, Gemini, Code Llama, and Wizard Coder have demonstrated impressive capabilities in this regard. However, we also encounter challenges, especially in the realm of source code summarization. It's noteworthy that many authors have not reported results in this area. Furthermore, there's evidence of poor performance in summarization capabilities. For instance, Octocoder reported a 0.00 shot pass at K performance on the Human Evil Explain benchmark for models like CodeGX2 and StarCoder. This highlights the need for further research and development in this field. In our study, we conducted a comprehensive performance review of open-sourced coding large language models, or LLMs. We compared their abilities in both text-to-code and code-to-text tasks. Our findings revealed that Magicoder, a DS6.7b model, excelled in explaining Python code. On the other hand, Wavecoder, another DS6.7b model, stood out for its code explaining capabilities across multiple languages. These insights are crucial as they shed light on the strengths of these models, paving the way for their effective utilization in various applications. In our exploration, we've delved into the performance of open-sourced large language models, or LLMs, particularly their proficiency in handling source code and natural language text. Our primary focus has been on their code-to-text capabilities, which is the ability to generate summaries or explanations of source code. This is a crucial aspect in understanding legacy code or creating documentation. As you can see in the figure, we've reviewed a variety of models, highlighting their connections and the families they belong to. However, it's worth noting that some models, like StarCoder and CodeGX2, are not discussed in detail due to their poor performance in code summarization. The advent of encoder-decoder architectures in natural language processing has opened up new avenues in software engineering, particularly in generating summaries of code. This is a significant development, as it aids in understanding legacy code and creating documentation, proving beneficial for working programmers. However, there's a noticeable gap in research focusing on code-to-text capabilities. Despite the potential of these models, we face certain challenges. There's a lack of reported results on source code summarization, which could be attributed to the possible poor quality of model summarization capabilities. This is a problem we need to address to fully harness the potential of these models in software engineering. We delve into the world of open-sourced large language models, or LLMs, and their significant role in software engineering. These models, such as GPT-4 and Gemini, have shown impressive capabilities in generating source code based on task descriptions and summarizing code. However, there's a need for more research and improvement in code summarization, an area that has seen less focus. To evaluate these models, we use specific metrics and benchmark datasets. For instance, Human Evil and Codex GLUE are used to measure code generation and explanation capabilities. But how well do these models perform? Let's look at some results. Magicoder, a DS6.7b model, stands out for its Python code explanation capabilities. On the other hand, Wavecoder, also a DS 6.7b model, excels across multiple languages. These findings highlight the potential of LLMs in software engineering and the need for further exploration in this field. Our research primarily focuses on the performance of open-sourced large language models, or LLMs, in handling source code. We're particularly interested in their code-to-text capabilities, which involve generating summaries or explanations of code. To investigate this, we've adopted a review-based approach, examining some of the leading open-sourced coding LLMs. We've delved into their capabilities, strengths, and weaknesses, providing a comprehensive overview of the current landscape. To evaluate these models, we've used a variety of metrics and benchmark datasets. These tools allow us to measure the model's performance in both code generation and explanation tasks. In the next part of our presentation, we'll be discussing these evaluation methods in more detail, as well as sharing some of our key findings. So let's dive in and explore the fascinating world of LLMs and their applications in software engineering. Our research utilized several benchmark datasets, including Human Evil, APPS, MBPP, DS1000, Codex, GLUE, and Human Evil Explain. We specifically used Codex GLUE for tasks like clone detection, code completion, and code search, with a focus on code summarization. Code SearchNet, a part of Codex GLUE, was instrumental in this, containing programs in multiple languages. We evaluated the summaries using the smoothed BLEU score. Now let's talk about our findings. The standout performers on the Human Evil Explain benchmark were Magicoder for Python and Wavecoder for multiple languages. However, we noticed a significant issue. Many authors did not report results on source code summarization. For instance, Octocoder reported a zero-shot pass at K-performance of 0.0 for both CodeGX2 and StarCoder. This highlights the need for more research and development in this area. Diving into the key results, we find that Magicoder, a DS 6.7b model, stands out in its ability to explain Python code. Meanwhile, Wavecoder, another DS 6.7b model, shines in explaining code across multiple languages. These findings underscore the potential of large language models, or LLMs, in code explanation tasks. Now, what do these results imply? Well, they suggest that certain LLMs possess strong capabilities for code explanation. This is significant because it means that LLMs can be effectively used for code summarization. This could be a game changer in understanding legacy code or creating documentation. However, it's not all rosy. In our studies, we found that not all models performed well. For instance, CodeGX2 and StarCoder showed poor performance on the Human Evil Explain benchmark. In fact, Octocoder reported a 0.00 shot pass at K-performance for these models. This highlights the need for further research and development in this area. Our investigation into open-sourced large language models, or LLMs, has primarily focused on their code-to-text capabilities. We've examined how these models handle source code in relation to natural language text. Encoder-decoder architectures have been instrumental in this process, proving their worth in software engineering tasks, particularly in generating code summaries. We've seen the capabilities of various LLMs, including GPT-4, Gemini, CodeLlama, and WizardCoder. These models have shown impressive abilities in generating source code and natural language summaries. To measure these capabilities, we've used a variety of benchmarking datasets. These include Human Evil, APPS, MBPP, DS1000, Codex, GLUE, and Human Evil Explain. These datasets have been invaluable in assessing the code generation and explanation capabilities of these LLMs. In conclusion, the application of LLMs in software engineering particularly in tasks involving code-to-text translation, has shown promising results. However, there is still much to explore and improve in this exciting field. Our investigation has revealed a significant gap in the field of source code summarization. It's noteworthy that many authors have not reported their results in this area. This could potentially be attributed to the poor quality of the model's summarization capabilities. Turning our attention to open-sourced coding large language models, we've conducted a comprehensive review of their performance on both text-to-code and code-to-text tasks. We've utilized a variety of evaluation metrics and benchmark datasets in our analysis. In conclusion, while there are impressive strides being made in the field, there's still much room for improvement, particularly in the area of source code summarization. This presents an exciting opportunity for future research,